Log on, tune in, find out. Another good idea from Cambridge.
Okay, so today we have Sasha Borovic from Manchester, who will tell us about finite groups, black box groups, and algebraic groups. And then after the seminar, at 5:30, we'll meet in front of the reception and go out for drinks or something, if you're interested, so you're welcome to join. And then, just an announcement, so next week there's no seminar on Tuesday, and then we'll meet again next Thursday. So, okay.
My talk is motivated by questions in model theory. And these motivations are mostly hidden in the talk. I will discuss only those aspects of the theory which directly face theory of algebraic groups and theory of finite groups. And so for that reason, I will have to start with the explanation still of a little bit of model theoretic concept, just a tiny bit, and to set up the context of the questions. I will discuss classification of finite simple groups, among other things, and we'll discuss so-called black box groups methods. These are probabilistic methods for computations in finite groups, Monte Carlo methods for computing in very big finite groups, and relations with algebraic groups of various kind. I start perhaps with the concept from model theory, uncountable categoricity and categoricity in general. So essentially, in model theory, we describe algebraic objects by formulae of first-order language, or the language of predicate calculus. We can write formulae using algebraic symbols, symbols for variables and quantifiers. If formula is closed, if every variable is bound by a quantifier, then we can say whether this formula is true or not in a particular group, for example. For example, for every x, for every y, xy equals yx means commutativity. For all x and for all y, product xy equals product yx. Simple example. When we have a group, we can say, in principle, decide whether the group is commutative or not commutative. So when we have some algebraic structure, for example, a group, I will talk about groups and fields almost exclusively. Then we can write the set of all first-order formulae in the language of groups, which means using symbols for multiplication, for inversion, equality, and quantifiers. We can write formulae, closed formulae, and consider the set of all formulae which are true in the given group. This form a set of formulae. The set of formulae is consistent because you cannot derive a contradiction, a model. This group exists. The set of formulae is called the elementary theory. Elementary theory is complete in the sense that every formula, every closed formula either belongs, either formula or its negation belongs to theory. Obviously, because every formula is either true or false on a given group. So, elementary theory of a group or a field is a very good logical object, a complete, consistent theory. And we say that two groups are elementary equivalent, and symbols is used, if they have the same theories. Basically, it means that they're undistinguishable from logical point of view. They have exactly the same theories. At the level of logic, we cannot distinguish them. And a group or a field is called Aleph-1 categorical if there is a group of cardinality Aleph-1 such that it is elementary equivalent to this group. And moreover, it is unique. Existence is not a problem, uniqueness is a problem. Why Aleph-1? Well, because simply it is shorter to write than uncountable. There is a theorem by Morley. If something is categorical in one uncountable cardinality, it is uncountable in all. So Aleph-1 here does not play any specific role any uncountable cardinal can be used instead of it. Well, examples, yes? Yes, elementary equivalent and uncountable to it. I will give an example. The group of rationals with respect to addition, obviously countable group, but it is only one categorical. For the following reason, we can write not the whole theory, but at least sufficiently many axioms, which express commutativity, the very first axiom. I use multiplicative notation, although group is additive. The next axiom says that there is no elements of order 2, no elements of order 3, and so on. It is an infinite set of axioms for every n. There is no torsion. And then next group of axioms, that there are roots of every possible degree. It is divisible. Well, any group which is elementary equivalent to group of rationals with addition will be a divisible torsion-free group. So it is a vector field over rational numbers, and it is uniquely determined by the size of its basis. In first uncountable cardinality, it means that the basis has to be of cardinality L1, and hence there is only one such vector space. So although a group is countable, it is uncountably categorical. And the model, well, we can take some well-known group, for example, the group of positive real numbers with respect to multiplication. It is uncountable, divisible, torsion-free group. It is elementary equivalent to a group of rationals. So a simple example, it is a relatively trivial example. Much more interesting are observation that every algebraically closed field is L1 categorical. It follows simply from the standard structural theory for algebraically closed field that any of them can be obtained by taking algebraic closure of the prime field, purely transcendental extension, and then again algebraic closure. So everything boils down to the size of transcendental basis. And therefore, in every characteristic, there is just one algebraically closed field of cardinality continuum, say. So this is why complex numbers are complex numbers. They are unique in that sense. It can be shown that, and the word simple algebraic group appears here first in the game, that simple algebraic groups of algebraically closed fields are also L1 categorical. The old theorem by McIntyre says that L1 categorical fields are algebraically closed. And there is an old conjecture by Zilber that the same is true about simple groups. Simple L1 categorical groups are algebraic groups of algebraically closed fields. This conjecture is proven in some cases. In particular, just this year, I with two of my colleagues published a book, 400-something pages, containing a proof of single theorem. Confirmation of Zilber's conjecture in case when we have a simple L1 categorical group which looks like algebraic groups in characteristic 2 in the sense that it has infinite elementary abelian 2 subgroup. Then it is indeed a simple algebraic group of a field of characteristic 2. So in partial cases it is proven. It looks like it might be close to be truth. And when you look at the whole thing, then it appears that the role of simple algebraic groups is that, first of all, they have exceptionally good description by first-order formulae, exceptionally complete description, that logic says everything about them. And secondly, they are characterized by this property. They are indeed exceptionally unique in the world. This is, of course, appear the word you have to keep in mind, because this is still pretty conjecture. Zilber's conjecture is not proven in full form. My question is here, what is this description? And what is a reasonable finite description, a usable description? And here we encounter a problem which was well known to even to ancient Greek, classical Greek philosophers. The problem is that we in mathematics are happy to live with just any definition and any description, and not always caring about what are good ones. And I will give you examples fairly soon. Let us move to finite groups for a second. PSL to Q, Q odd, Q bigger than 3, a simple group, suggest a formula which defines it in the class of finite groups. Write a formula such that if a group is finite and this formula is true, this is PSL to Q. Well, and you instantly discover that to write this formula you have to use huge amount of information coming from classification of finite simple groups. Instantly. For example, you can write this thing. First of all, we want to make it simple. Okay? So we can assume that G has no abelian normal subgroups. This is the first order property. No abelian normal subgroups means that for every non-trivial element, there is a conjugate of this element which does not commute with the first one. It can be written by a formula. It can easily be written by a simple formula that every element is a commutator. It can be written by a slightly tricky formula. The centralizer of elements of bigger than 4 is abelian. If you know classification of finite simple groups or just properties of Chevalier groups, for example, for finite fields, you may think for a second and try to decide whether it is enough or not. It looks almost enough until we notice that alternating group on 7 letters also satisfies these 3 conditions. So we have to add more properties. And so essentially, when you work with finite groups at the level of their logical description, you are in position when to justify this logical description, you have to use full strength of a classification of finite simple groups. And these descriptions are exceptionally unnatural. Because what is natural in these 3 axioms, which I just started to write from the top of my head, trying to make group as small as possible. Classics, in this case, they apparently, yes, already encountered this problem. And there is a famous story in history of classic philosophy about Diogenes, who refuted Plato's definition of a man as a two-legged animal without feathers by producing a cock with feathers pulled out. But Plato was not a person too easy, to get an easy victory off, because he added to this definition with broad, flat nails. What we did with PSL2 in the previous examples was exactly this addition of broad, flat nails, of addition something even more natural and more random, just to make object uniquely described. So there is something wrong with the logical information which is produced by classification of finite simple groups. We need to somehow systematize it in order to understand what is happening in this theory, in theory of simple algebraic groups, in the theory of finite simple groups, from logical point of view. Well, I argue that the core of the theory for finite groups of Lie types, for algebraic groups of various types, Curtis' theorem and its manipulation. This is in effect a description of a simple algebraic group as an amalgam, as a group generated by root SL2 subgroups. So we consider the set of root SL2 subgroups. So in effect, these are subgroups generated by 2 root subgroups. They are SL2 or PSL2, corresponding to a simple root in a simple root system. So we have a Dynkin diagram which lists simple roots. For every Dynkin diagram we have SL2. And you can see the 2 root SL2s generate something simple and small according to number of nodes between the links between the 2 nodes of the diagram. If there are no nodes, they commute element-wise and generates a central product. If there is just one link bond, then it is PSL3. If two bonds, it is PSP4. And a bit more accurate details about embeddings of root SL2s within these things generated. They have to be embedded as root SL2s on these small rank 2 groups. And then anything generated by this system of SL2s is isomorphic actually to a Chevalier group with the corresponding Dynkin diagram. So in case of algebraically closed fields and algebraic groups, Chevalier groups, it is exactly. Curtis's theorem is heavily used in classification of finite simple groups. And it is one of the core instruments of identification of finite simple groups with corresponding algebraic groups over finite fields. And one can observe that Dynkin diagram is actually a first order property. It can be written by pretty long by a formula of predicate calculus. And this is a pretty peculiar formula because it happened that this method, this machinery works in some area of computational group theory, so-called black box group theory. So I'm leaving the realm of first uncountable cardinality and move to finite objects. So black box group, well, it is just well established actually now term for description of a process of sampling of elements in a group in which we do computations with random elements and try to determine the nature of the group. So it is considered as being as some kind of device or algorithm which produces random elements from a finite group. We assume that this black box is sufficiently good that its elements are independent, which is almost never true, and that they're uniformly distributed, which is more or less true. But anyway, our task is to determine the group X from the sample of random elements. This is again a highly technical task and uses classification of finite simple groups heavily. And in the same time, this is essentially the only available tool. However, it appeared, approach appeared actually much earlier, and in its commutative version, it is, for example, Miller-Rabin primality test, because determining whether a given number n is prime or not can be considered as a black box problem. We do calculations in the multiplicative. We multiply integers modulo n. It is something which is easy to implement. You use your favorite random number generators for producing random elements. You really do have black box group. If your random number generator is good, you can believe that your elements are uniformly distributed, independent, and whichever. Okay? You can multiply them. You can compare them. And the question is whether this group is isomorphic to the additive group, model n-1, to the cyclic group of the n-1. Because this is a characteristic property of prime order elements. This is a typical black box problem. You have black box group, you have some known group. You have to compare to decide whether they are isomorphic or not by looking at random sample of elements and doing something with this random sample of elements. In non-commutative version, the most important area of applications is computations with big matrix groups. Imagine we have two matrices of size, say 100 times 100 over any finite field. They generate something. You may wish to determine what they generate. Linear algebra allows to determine that this group, for example, matrix group is irreducible, absolutely irreducible, tensor indecomposable maybe. And basically it looks like it is simple, more or less. For example, you know that. You want to determine the name of this group. The group is of astronomical size. 100 times 100 already ensures that the number of elements in the group is bigger than the number of electrons in the visible part of the universe and whichever. So there is no any way of doing any deterministic calculation. The only known approach is random sampling, which is a separate story, which I'm not touching here at all. It is a deep theory with deep connections to ergodic theory, for example. And then we have to look at properties of these elements or combinations of these elements and try to test some first-order formula which would identify X. Existence or non-existence of elements of a particular color order is an example of such property. If, for example, you want to compare a group with given group, and we found here an element of order which is not present here, you automatically know that this is different from a target group. Yeah. So it is one of these properties, with the exception that it is technically infeasible to determine a multiplicative order of a big matrix of a finite field. The problem involves either discrete logarithm or factorization of big integers into primes. There is no efficient method. So there are some tricks around. There is some play going around this thing, which is pretty interesting, which I unfortunately will not have time to discuss, because, well, because actually already at that level, it becomes apparent that actually the actual calculation in which the whole thing is taking place is not a finite group. And we calculate in some other object. We only think that we calculate here in that thing. You will see later, but I will remind you that this problem about orders. Well, there is yet another unique, actually, difficulty with these two series of groups, Bn and Cn, in odd characteristic. They are undistinguishable by orders of elements, in the sense that they are undistinguishable in polynomial times. There is a subtle difference, but it is exponentially small and undetectable in polynomial time by random sampling. Why Q odd? Because when Q is even, they are, of course, just isomorphic. Interestingly, when Q odd, these two groups have the same orders. This is an example of different infinite series of finite simple groups, non-isomorphic, but of the same order for every Q. Orthogonal group and projective Simpleki group in odd characteristic. It is interesting to look at why the statistic fails. First of all, because when we compute in a group of a matrix group of a very large finite field, say prime field of order P, unipotent elements appear with probability about 1 over P, simply because regular semi-simple elements form an open subset in the simple algebraic group. They dominate the whole thing. They become invisible, unipotent elements. In particular, if we consider a matrix group in characteristic 2, it starts to violate Phi-Thompson theorem. It contains no involutions, in the sense that you can do whichever you wish with this group, but you will never find a concrete involution. They are so rare and so invisible. They just disappeared from the screen. So unipotent elements disappear from the screen. We are working in an anisotropic group, although we are in the finite domain. No unipotent elements. Well, when you look at statistical orders of regular semi-simple elements, you see instantly that since every regular semi-simple element, its centralizer is maximal torus, and essentially statistics of orders of regular semi-simple elements is the statistics of orders of maximal tori. And this is entirely controlled by first cohomology of by Galois cohomology in the Weil group, and essentially everything boils down to the Dynkin diagram. And the statistic is controlled by Dynkin diagram. Dynkin diagram is the same in Bn and Cn. So there is no way around it. However, but if we look at involutions and its centralizers, we discover that the conjugacy classes of involutions and structure of their centralizers is controlled by extended Dynkin diagrams, and they are different. And actually, one interesting thing, that extended Dynkin diagrams of these groups is a first order property, not only Dynkin diagrams, but extended Dynkin diagrams. And moreover, this is a first order property which is checkable in realistic polynomial time, in the case of black box groups. Unlike presence, for example, of unipotent elements. It is. For that, we have to construct involutions. Well, first of all, when we have in a group of odd characteristics, we have abundance of elements of even order. And as soon as we have an element of even order, by square and multiply methods, we eventually can get an involution. And this works in polynomial time. So there is no serious time restrictions here. And this polynomial, this exponentiation is actually comes from Miller-Rabin primality test. This is why it was first used systematically 30 years ago. When we have an involution, we can construct its centralizer by using the following partial map. It is a very strange map. We take a random element from the group, element produced by a black box, do the following manipulation with it. We conjugate involution by this element, multiply with it, compute square root, which can be computed if we know the global exponent of the group. And its odd part, it is a computation is feasible. It works if a product of two involutions is of odd order. It is okay. And it can be explained why it works, actually. It works the following way. We have involution, and it's a random conjugate. Okay, we take their product. Two involutions generate a dihedral group. They invert their product. Okay. So if the product is of odd order, then in this dihedral group, these two involutions are Sylow subgroups. They conjugate by an element from the cyclic group generated by their product. Basically, they are conjugate actually by square root of the product, as one can easily see. So this involution was sent by something x. We take square root and conjugate it back. The composition of two conjugations does not move. Involution belongs to the centralizer. Actually, this trick was invented by Élie Cartan, interestingly. And if you apply it to a group, for example, special linear group over real numbers for x, and the involution T inverse transpose involution, you will see that this defines a map from the Lie from the SLN onto orthogonal group. And this map was used by Cartan for proving connectedness of the orthogonal group. And what is written here is nothing else but the composition of arbitrary real matrix as a product as orthogonal matrix and symmetric, positive symmetric matrix, the square root. So this is actually a pretty classical thing and comes from theory of Lie groups from real classics. Well, the whole thing works because this map happens to be equivariant under the action by elements from the centralizer of involution. The simple calculations show that if we multiply argument by arbitrary element from centralizer on the left, the result is being multiplied contravariantly by inverse of it on the right. So, which ensures uniformness. If X indeed produces uniformly distributed elements, okay, this map produces uniformly distributed elements in the centralizer. Black box in group produces black box in the centralizer. So, some applications of that trick were developed by Parker and Wilson, and independently by my student, Shukrul Shinkaya. Well, he's no longer a student. It was used for solving a notorious problem in the theory of computational algebra. When you have a matrix group of a field of characteristic P, it is notoriously difficult to determine whether it has non-trivial unipotent radical. Again, for the same reason, unipotent elements are invisible. They are not present in the field of view. Constructing centralizers, however, and reducing problems to a problem in the centralized involution further allows to solve it. Actually, Shukr developed this trick for computing both a unipotent radical and factor model unipotent radical. And this is also a pretty interesting piece of work, because what is happening? That first of all, he reads Dynkin diagram of the factor by doing computations in the group and ignoring entirely the fact whether this group has unipotent radical or not. It is invisible anyway. We just compute. And the unipotent radical is so tiny, it just never pops up in computation. You can simply ignore it. It is too small. So as a result, after that, he finds, in effect, Dynkin courtesy system associated. Interestingly, to do that, one has to work, first of all, with a single lone root SL2 subgroup. Again, we do not care whether this is a unipotent radical is present in what we work in or not. Maybe it is root SL2, maybe it is root SL2 on the top of some unipotent radical. Then, when you have a lone root SL2, it is possible to conjugate it a little bit, and some manipulations allow you to construct a standard Dynkin diagram. And identify the whole thing and ignore unipotent radicals at this stage. You construct Dynkin diagram and courtesy system above the factor. Remarkably, this setup, working with a lone root SL2 with perhaps some unipotent radical underneath, is exactly setup of classical involution theorem of Ashbacher. He works with them, again, ignoring entirely this possible unipotent radical. It is present in notation throughout his paper, but he never makes any use of it. It's simply ignored. It is exactly computational, probabilistic version of Ashbacher's classical involution theorem, one of the fundamental theorems in the classification of finite simple groups. There are also actually quite a lot of stuff which comes from here, that when you start working with it, occasionally you, and very frequently actually, oh sorry, it has to be q to minus 1 to n, of course, to power n, not n. Split maximal Tarai, they may have different orders. And in many groups, for example, maximal Tarai, which is split or almost split, have orders of q to minus 2n or q plus 1 to n. All that actually pop-ups in calculations and courtesy systems associated with non-split torus of order q plus 1 to n. It's quite interesting and beautiful. It's quite a lot of beautiful configurations arise here. And after you have courtesy system, when you have a complete system of root SL2s for doing that, you can do quite a lot of stuff. You can produce involution framing conjugacy class. You can construct all subsystem subgroups. You can construct array of different kind, and such things. Remarkably, all this computation can be done without without encountering a unipotent element, working only strictly with semi-simple elements. And secondly, the structure of algorithm entirely ignores the underlying field. It does not matter. It does not depend on the underlying field. We never got actual generators for this SL2, root SL2. Canonical generators are two unipotent elements when you look at Steinberg presentation. We never get to them. We work with this SL2s instead of elements. And the field is not present. And we work as if we are working in an anisotropic group. We never have unipotent elements. We work as if we are working in a compact Lie group, for example. Structurally, it is a very interesting picture. It is completely different landscape from what it is normally happening in finite group theory. Finite anisotropic groups. Well, if we return back to uncountably categorical groups, you see that a version of Curtis's theorem is featured prominently and actually a key result in what was done so far. And this is happening because it is relatively simple first order formula. And it is easy to control formula. Moreover, it is exactly the same formula in effect as in finite groups or in the black box groups. There is no difference in that. It is something which unites all three theories together. The nature of this formula, exactly because field is not present in it. And well, however, it's still not an explanation why it appears in black box group theory. Because we know that something to appear in black group theory, you have to appear sufficiently frequently. This is a probabilistic thing. We have to be lucky to get it. And it is happening because actually the formula is robust. It remains true in a version of probabilistic logic where quantifiers are understood as almost all or sufficiently many with a non-zero probability. And so there is some kind of probabilistic logic sitting inside. And we can try to understand what is this probabilistic logic. As I said, that we are computing not in a finite group, in something else. Since field does not matter, it looks like we compute simultaneously in a Chevalier group over all finite fields of the same characteristic, or maybe even of different characteristics. And so for that reason, we are working in some trick, some kind of object which is glued from all these finite groups in the ultra product of these things. When we have an ultra product, then this ultra product, first of all, it has the property that if a formula is true on every group in the product, then it is true on the result, on the ultra product. And so as a result, we are working in a group which is called a pseudo-finite group in model theory. Pseudo-finite group is a group which is a model of a theory of finite groups. It is a group such that every formula which is true on it is true on some finite group also. And when we have a pseudo-finite group, especially of the special kind like ultra products of finite groups, we have a measure, because on every group we have a standard probabilistic measure, discrete measure. Okay, we take the ultra product, we get a measure with values in the ultra product of rational numbers in the non-standard, in the sense of the non-standard analysis in some extension of real numbers, but still it is a measure. We can take standard part of it and consider standard measure which appears here. So this thing comes with measure. I want to comment on the pseudo-finite field which appears inside of the group. It will happen to be of characteristic 0. We take ultra product of fields of different characteristics. The result is characteristic 0. It's smoothed out. Well, pseudo-finite groups are not well understood yet. Pseudo-finite fields are perfectly understood. A field is pseudo-finite. It is elementary equivalent to ultra product of finite fields. So is a model of a theory of finite fields. If and only if it satisfies three conditions which are instantly recognizable as properties of Galois fields, finite fields. They are perfect. They have unique extension of each degree. and they are pseudo-algebraically closed. Irreducible variety of a field has a point in that field. So simple algebraic characterization, it is a very nice class of fields, best possible in a sense, in many aspects. It is just a very big finite Galois field. Very big in the sense that it becomes infinite. Well, again, when I talk about probability, is because what is happening, that although many important formulae, well, we do not have any probability in simple algebraic fields or algebraically closed fields already. You know, and formulae there have to be true absolutely, with probability 1 in effect. So in effect, we are looking at the formulae we use for our characterization formulae which are true with probability 1. But in the same time, the picture is not black and white. It is not just 0, 1 case when everything happens with probability 0 and 1, because in the intermediate steps, we are getting sets and formulae which are true with intermediate probability. Typical example, when you are trying to describe the property being an even element, an element of even order, it is not a first order property. We replace it by some approximation, which is a pretty good approximation. The center of the centralizer of this element contains an involution, which as one can easily see automatically true if X is of even order. And if we look at group PSL2, this property holds there with probability 1/2. Well, simply because there are two tori, Q minus 1/2 and Q plus 1/2. And so for that reason, this is where 1/2 comes from. So it is a very delicate situation. And this, however, is more than just curious observation, because actually it looks that these observations, they confirm on the line conjecture, very serious conjecture, which is becoming central in all this theory, put forward by Udi Khrushchevsky in about 1997, I believe, but only now we really have technique to do something about it. That we have so-called a generic automorphism. Well, I do not want to give the definition, but, well, generic in the sense, and indeed very generic. Well, in sense of algebraic geometry, roughly speaking, yes. Generic automorphism of simple uncuttable categorical group, then the group of fixed points and pseudo-finite. In real life, if Zilber's conjecture is true, and we have group G, algebraic group of algebraically closed field, and its generic automorphism, then generic automorphism of algebraically closed field, which is in effect, because automorphism of simple algebraic groups are in effect field automorphisms. And, by result of Khrushchevsky, this is a generalized Frobenius. This is an ultra product of finite Frobenius maps, you know, from this value which I use in construction of finite Lie groups of Lie type in Steinberg's construction. And the group of exponents is, of course, a pseudo-finite field. It is true in algebraic groups. Remarkably. Moreover, Khrushchevsky puts forward an interesting intermediate conjecture, which is confirmed him not for groups but for some simpler structures. That if we have a generic automorphism, then before we proving that this is a pseudo-finite group, we are proving that there is a good probabilistic measure, which behaves nicely with respect to logical formulae and logical properties. So that formulae and can be measured by size of to what extent they are true, by probability to which they are satisfied. And which, of course, instantly brings to mind black box groups. And the whole thing here starts to look like black box groups, the strange computational theory, which is done for purely technical purpose of calculations in gap and magma. It sits in between theory of finite simple groups and these ground theories and model theory, like uncountable categorical group. It is a bridge between the two. And when you look at the black box group theory, then in this context, it looks like it is some fragment of the following theory. We have a pseudo-finite group with the standard probabilistic measure. We have a bit more exponential maps. We raise things to power or not to, but to any supernatural number, which is in effect brings us to mind that order of an element in a black box group is meaningless because we cannot determine it anyway, which was given at technical level, and which can be written by formulae with quantifiers, of that kind, with checkable, probabilistically checkable formulae. This is one observation. Another observation is that actually there is a number of technical results which partially confirm Khrushchevsky's conjecture or move in the direction of the Khrushchevsky conjecture. They mostly belong to my student Pinar Ugurlu. And one of things, tight atomorphism is just some by some abstract property of generic atomorphism, which is introduced just to get purely algebraic setup, to remove unnecessary model theory from consideration. If a group of fixed points is pseudo-finite, then she proved that G is a simple algebraic group of algebraically closed field. Her proofs uses heavily classification of finite simple groups. But first I have to give explanation of the tight atomorphism. Automorphism is tight simply means that if we have an invariant definable subgroup and a group of fixed points, and then take, roughly speaking, definable closure or the risky closure, of the group of fixed points, we get the whole subgroup. Frobenius map, for example, if you consider generalized Frobenius, or basically almost any automorphism is tight in algebraic groups, field automorphism. If we have defined a Zariski closed invariant subgroup and a group of fixed points, then the Zariski closure of the group of fixed points is the whole subgroup. So no more than that. It is a natural and not very restrictive assumption. As soon as we have automorphism with a group of fixed points pseudo-finite, in this model theoretic setup of uncountable categorical group, everything remarkably becomes simple algebraic. What is used in the proof? Two results model classification of finite simple groups. One of them is a theorem of John Wilson, classification of simple pseudo-finite groups. Model classification, he proved that they are Chevalier groups of pseudo-finite fields. Well, he proved that they yes, Wilson proved the elementary equivalent, but actually, I believe Francois Point proved that it is actually isomorphic to some appropriate pseudo-finite field, to group of pseudo-finite field. And Ugurlu proved the same thing with important difference. Well, it is a technical difference of word. John Wilson assumes that the group is absolutely simple. There are no normal subgroups whatsoever. Pinar uses only assumption that there are no definable simple subgroups. There is a crucial difference because there are definably simple but not simple pseudo-finite groups. So it is important difference. Finiteness condition, which is used is the descending chain condition for centralizers, which is automatically satisfied in our context. Again, her theorem uses classification of finite simple groups. I do not like to use classification of finite simple groups. Her intermediate result is free from classification of finite simple groups. however, she proved that under these assumptions, if we have, oh no, sorry, this is the way it sits, on the contrary. That inside we have a Chevalier group. Yes, it did. This is how it appears, the previous theorem. Here, so this is again classification of finite simple group sets. But I want to say, to make a bold observation that actually it is clear already, and that these results can be proven without the use of classification of finite simple groups. Classification of finite simple groups can be eliminated from it. It be attending some absolute status in the sense that it links finite simple groups with infinite groups without using machinery of finite, without using results about finite. So this bridge, between finite and infinite in the theory of simple algebraic groups gets sounder foundation. And basically, it looks like Khrushchevsky program fits incredibly well with the classification of finite simple groups, and methods of classification of finite simple groups can be used there. And unfortunately, I have no time again to talk about that, but slightly result under slightly stronger assumption. When we make assumption, which was done before, about tightness of pseudophytes, not only because one alpha, but also about all its powers, which automatically happens in the case of generic anamorphism, by the way, and the case of generalized Frobenius, because if we have generalized Frobenius, and its power is again generalized Frobenius. It says that in this context, this is a simple algebraic group. This definitely can be proven without classification of finite simple groups. It doesn't use the result of classification of finite simple groups. It uses some ideas and methods, and some interesting, deep, and beautiful ideas from that theory. So, remarkably, this link does exist. And one interesting thing that happens here about this strange discipline, because it is not a theory, it is a computational, how to say it, a technology. In a sense, theory of black box groups and black box groups algorithms. It actually fits between model theory and finite group theory with the exceptional precision. It looks as if it was always made for being there, I love to say the Russian proverbial saying that it gets into place like a cartridge into the lock of a rifle. With complete precision. So, it is something really interesting might happen here in the future. In the area of interact model theory, finite group theory, theory of algebraic groups, and maybe something else, theory of fields and model theory of fields, and a lot of other stuff. And so it is a pretty interesting synthetic area, which is currently is being developed quite intensively. So thanks for your attention.
So what's FMR? Maybe you said that.
Oh God, sorry. Uncountably categorical.
Okay.
Yes, uncountably categorical. I tried to remove it everywhere in every place, but only one categorical. Yes, sorry. Yes, I have to make this correction. So model theories prefer to use the term finite Morley rank. It is easier to use, but longer to define. But it's strictly equivalent.
Oh, okay.
Yes, to uncountably categorical for simple groups. Yes.
So if you have groups that are isomorphic but not equivalent.
Sorry?
If you've got two groups that are isomorphic.
They are automatically equivalent, of course.
So if you've got two non-isomorphic groups which are
Two non-isomorphic groups. Yes, of course.
no, well, I says, can you have two countable non-isomorphic but equivalent groups, say? Or do they have to have one of them? Your example was one of them.
Yes, of course. You can take, for example, a group of rational numbers and direct product of two copies of the group of rational numbers. They're equivalent but not isomorphic. In that sense.
So when you were discussing that example, you said that so anything which is equivalent to the rational numbers has to be torsion-free and divisible. So
Yes.
that's clear.
And that's
is
it.
Obvious from that something which is a vector space over the rationals is equivalent to the rationals, or does that take?
Yes, of course. You are quite right. This still has to be proven. Yes, it can be proven. And it requires some work. I was slightly cheating because I was showing just one direction. Because I was writing just one bit of a theory, just some list of axioms. But I never claimed or checked that this is a complete list, in a sense. So some additional work has to be done, perhaps.
So I have another question. So you said that a Dinkin diagram is a first-order
Property.
So can
In
you say
simple
what that
algebraic
means?
groups. Sorry?
So what does, because a Dinkin diagram doesn't seem like it's a statement about elements of a group. Or
Yes.
it is a statement about elements.
Yes, basically, the trick here is that you define a root SL2 subgroup in terms of its central involution.
Okay.
You start with saying that there is an involution, an element of order 2 such that in its centralizer there is a normal subgroup which looks like or elementary equivalent to SL2, and you write list of axioms which define property of being SL2, and such some other properties. And then there is another such that two together, they generate. And what is important, the words they generate can be written using only finitely many products, because generation is bounded. To generate SL3 by 2 root SL2s, you have to take relatively short products, of length 3 or 4. So all that becomes actually, the resulting formula, of course, it takes maybe a page to write, but it is of very transparent nature. Actually, it is readable and it is meaningful. It is not like examples with this cock without feathers, which I showed you in the beginning.
Other questions? So maybe we can thank the speaker again.
Thank you.